All right, let's get right into it. Imagine a classic detective story for a second, where the crucial clues in some old unsolved case are being mysteriously corrupted. Well, we're about to dive into a real-life version of that story. Only this mystery is unfolding right now in the world of cancer research. And the clues? Well, they're hidden inside our own DNA.
So, what if that's the case? I mean, it's a huge question, right? We rely so much on studying diseases from the past to figure out cures for the future. But what if that historical record? What if it's flawed? Today, we're going to uncover how a hidden chemical process has been creating false leads for years, and more importantly, how scientists have finally cracked the case.
So, to really get a handle on the problem, we first need to take a trip to the library where all these clues are stored. But this isn't a library full of books, it's a library of human tissue.
You see, for decades, whenever doctors would take a tissue sample, a biopsy, they'd preserve it. These samples, called formalin-fixed paraffin-embedded samples, or FFPE for short, have built up into this absolutely massive historical archive. We're talking millions of samples that researchers can pull from to study how diseases like cancer have evolved over time. It is a literal goldmine of information.
But here is the major twist in our detective story. The very chemical that allowed us to build this incredible library, turns out it's also the prime suspect in corrupting the evidence locked inside.
So the chemical is called formalin, and it's amazing at preserving the structure of tissue, which is exactly why it's been the go-to standard for so long. But it has a dark side. Over time, it actually damages the DNA inside those cells, and in doing so, it creates what are basically fake genetic mutations. It's like it preserves the book perfectly, but scribbles typos all over the pages.
So how exactly does this happen? Well, it's a bit of sneaky chemistry. The formalin damages one of the 4 letters of our DNA code, C for cytosine, and it chemically morphs it into a letter that just doesn't belong there, U for uracil. Now, when a high-tech sequencing machine comes along to read the DNA, it sees this U and gets confused. It misreads it as a T. So what was originally a C is now recorded as a T. It's a total fabrication, a chemical ghost, not a real genetic change. In a detective novel, a false clue just sends you down the wrong path, wasting precious time. In cancer research, the stakes are so much higher.
And this is the critical difference right here. A true mutation is a real biological signal. It's a breadcrumb, a genuine clue that could lead to a breakthrough. But an artifactual mutation, that's just noise. It's a ghost in the machine, a false lead that can send researchers on a total wild goose chase, wasting money, time, and talent trying to figure out a mutation that was never even there to begin with.
And listen, this isn't some rare 1 in a million problem. The data is, well, it's pretty shocking. On average, these chemical typos can make up over 73% of all the new, low-frequency mutations found in a sample. Let that sink in for a second. That means almost 3 out of every 4 new clues a scientist might find could be completely false. That is a staggering amount of noise to sift through.
This whole issue becomes even more critical when you're working with certain kinds of samples. Imagine you're dealing with a tiny, irreplaceable tumor biopsy. The amount of DNA you can get is already incredibly small. In that tiny sample, the signal from all these fake mutations gets even louder compared to the real ones. So here's the bottom line. Without a way to clean up this data, these precious samples could be totally unusable. Okay, so if you're faced with a crime scene that's just contaminated with false evidence, what do? You need a new forensic tool to clean it all up, and that is exactly what scientists have developed. The real breakthrough here isn't some super complex software that tries to guess what's real and what's fake after the fact. No, it's a new chemical process that physically cleans the DNA, literally removing the false evidence before anyone even analyzes it.
So how does this new workflow actually clean the evidence? Well, after the usual prep steps, the real magic happens in step 3. Scientists found an enzyme that specifically hunts down and destroys those rogue uracil bases. The U's created by the formalin damage. It's like a biological search and destroy mission that just targets the typos, erasing them from the DNA before the sequencing machine ever gets a chance to see them and make a mistake.
And to make sure this super precise cleanup job can be done over and over again, reliably and on a big scale, the whole thing can be automated. Instruments just like this QIA cube make sure that every single sample gets the exact same treatment, which removes human error and makes the results something you can really trust.
Okay, so the theory sounds great. A new forensic tool, a clean crime scene, but does it actually work in practice? Well, the proof, as they say, is in the data.
And honestly, the results are nothing short of stunning.
This chart compares the old method to the new one. With a standard kit, scientists were finding around 120 potential mutations. But with the new gene-read kit, that number absolutely plummets to just 10. That's a 90% reduction in noise. All of a sudden, the real signal just got a whole lot clearer.
But that's the million-dollar question, isn't it? It's awesome to remove all that noise, but you have to be 100% sure you aren't accidentally throwing away the real clues, too. Is this new tool a precision scalpel, or is it just a sledgehammer? Okay, this right here, this table is the smoking gun. See these mutations? They're all listed in the official cosmic database of cancer mutations. So with the old method, they pop right up. A researcher would absolutely think, aha, I've found something important. But then, look over at that last column. After the new cleanup process, their frequency drops to 0. Zilch. They just vanish. This is the ultimate proof that they were never real to begin with. Just ghosts, created by the preservation chemical itself.
And this is what confirms the tool is indeed a scalpel. The data shows, plain as day, that while all those low-frequency fake C to T mutations get wiped out, the high-frequency real C to T mutations are left completely untouched. The process is precise. It cleans out the junk and keeps the treasure.
So what's the final verdict? Honestly, this is a massive leap forward. It means cancer research as a whole becomes more accurate. It means those tiny, precious samples sitting in biobanks are now more valuable than ever before. Researchers can finally stop wasting time chasing ghosts in the data and focus on real biological targets. And because the fix is chemical, not computational, it makes the entire analysis pipeline simpler, which could ultimately lead to faster, more reliable diagnosis for patients. So by cleaning up the clues of the past, we've really opened up a much clearer path to the future. It really makes you wonder, doesn't it? With this newfound clarity, just how many other cold cases of medicine are we now finally equipped to solve?